First thing is that solutions, when they're stored, that is, if I have, say, an acid, which normally is something that's in aqueous solution, and I am storing that in my chemical supply closet, typically you're going to store them in highly concentrated forms. The reason being that if you store it something at a low concentration, that means it has a very large amount of solvent and a very small amount of solute. And so typically when you're storing a solution, you're basically trying to store the solute more than the solvent. If I store some very, very dilute hydrochloric acid, I'm basically storing a lot of water because the solvent's water. And that's not particularly very useful for me. I'm really interested in storing the hydrochloric acid. By storing a very concentrated form of that acid, basically what I'm able to do is that I can store much more acid in the sense of more hydrochloric, hydrogen chloride, if you will, HCl, and less water. Another reason why I want to store concentrated solutions is it's very, very easy to take an existing concentrated solution and dilute it to a lower concentration, but it's relatively difficult to take a very low concentration thing and somehow pull the solvent out to make it more concentrated. So as a result, we store solutions in highly concentrated forms, and these highly concentrated forms are called stock solutions. And so anytime you ever hear about a stock solution, it's referring to a very concentrated form of that solution that's used mostly for storage. So these stock solutions, they generally have a higher concentration than is needed, or for acids, and often that is safe for laboratory reactions. The hydrochloric acid that I store typically tends to be 12 molar hydrochloric acid. 12 molar hydrochloric acid is way too high of a concentration for any lab that we would do here. And so when we use them for laboratory use, the solutions for laboratory use are therefore created by diluting stock solutions with more of the solvent to generate a more appropriate concentration. And so when I have this 12 molar hydrochloric acid, for a lab we probably would want something like 6 molar hydrochloric acid, and so I'll add water to the stock solution, to the 12 molar stock solution, to dilute it down to a 6 molar solution. And so that's basically the general idea of how solution preparation works. So let's take a little more look at that. And in order to calculate how much of our stock solution we need to use and how much water we need to add, we need to basically be able to do calculations on the dilution process. And so these dilution calculations are generally performed by setting up concentration equations for both the concentrated and for the dilute solutions. And so if I were setting up an equation here, if I was trying to go from my 12 molar to my 6 molar, I'd set up an equation for my 12 molar solution, and I'd set up one for my 6 molar solution. And I'd set these up, in this case, since they're both molarity, I'd set them up by basically, remember what the rule is for molarity, it's moles of solute over basically liters of solution. Okay? And then I do the same thing over here for my 6 molar. I'd basically say the number of moles of solute over the number of liters of solution for that thing right there. Okay? And so in the case of a dilution reaction, or a dilution case, when we're basically doing a dilution calculation, since dilution only requires adding solvent, the amount of solute in both equations is always the same. And so whatever moles of solute I had on this 12 molar and whatever moles of solute I have over here on the 6 molar, those are both going to be equal to each other. And so that's going to be a critical piece that's going to let us basically do these calculations. Because if those two things are equal, then we can basically solve for one of them and use that to find some piece of information for the other problem. Now, in most cases, this amount of solute that we have, that these two amounts that are equal that we talked about here, are generally unknown. And so is represented in each equation by the variable x normally, and the other unknown, whatever that is, will generally be a y. So typically, whenever we write this up, we'd say x mole solute here and x mole solute here, where both these x's are the same x. They're the same value. The reason why we generally don't know the moles of solute is that, if I take a bottle of hydrochloric acid down off the shelf, is that I could very easily measure what the mass of that solution is, or measure what the volume of that solution, but it's really difficult. In fact, I really have to do calculations to do it, difficult for me to measure how many moles of solute I have in a particular bottle, a particular amount of a certain solution. And so as a result, I very rarely ever know what that number of moles is unless I calculate it first. And we'll see a little bit of that as we go on here. So this is what we sort of have to start here. And so let's actually run through a couple of these going forward. So in this case right here, we have what volume of 12 molar stock hydrochloric acid solution, HCl solution, would be needed to make 3.4 liters of a 2.4 molar HCl solution. So first step here is we said we want to write out two equations. And so the first one, we have a 12 molar solution. And in the second one, we have a 2.4 molar solution. Okay. Now, once again, we remember that our definition of molarity was moles of solute over liters of solution. So let's look at the 12 molar solution here. Do we know how many moles of solute we have? It says nothing about that. And so as we said before, typically we'll put that we have X moles of our solute, which in this case is hydrochloric acid, HCl, on top, divided by our number of liters of solution. So how many liters of the 12 molar solution do we have? Well, looking at this, in fact, we don't know. In fact, it's a question. What volume? That's what we're looking for. And so we're going to call this Y. And so we'll say Y liters on bottom here. So 12 molar solution equals X over Y. Not really much information to go on there. So we'll take a look at our other guy over here. We'll sort of divide a little dividing line here. So 2.4 molar solution is our other guy. Do we know how many moles of solute we have? Nope, we do not. So once again, we have X moles on top, divided by the number of liters of solution. Do we know how many liters of the 2.4 molar solution we have? Yes, we do. 3.4 right here. So we'd say 3.4 liters down here. Now this guy, on the other hand, we can solve him because we're only missing that X right up there. And so we'll multiply 3.4 on both sides. And so if you it'll cancel over there on the right side. On the left side, though, we just say 2.4 times 3.4. Put that in the calculator, and I get 8.16. So I get that X is equal to 8.16 moles. But now that I know that this is 8.16 moles, I can go ahead and I can take that right there, and I can take my X and I can plug this guy back up into this guy right here. And so now, going ahead and rewriting this, I now have that my 12 molar solution is equal not to X over Y, but equal to 8.16 moles over Y liters. This one's now solvable. Multiply Y up on both sides. I get 12Y equals just 8.16 because the fact the Y's cancel over there on the right side. And so now I just want to divide both sides by 12. So doing this, we get that Y is equal to 8.16 divided by 12. So to get that divided by 12, I get 0.68. And so in this case, I get 0.68 liters of my 12 molar solution. To find significant figures that we originally up in this guy to start with, the 12 molar stock solution has 2 sig figs, the 2.4 has 2 sig figs, the 3.4 has 2 sig figs. That means that my X down here will have 2. That means that this guy will have 2. Since everything has 2, it means my final answer will have 2 sig figs, and so this is a good final answer. So I have 0.68 liters of my 12 molar stock solution would I need to create 3.4 liters of a 2.4 molar stock solution, or sorry, 2.4 molar hydrochloric acid solution. So if we're actually doing this, what we do is you take your 12 molar solution, you'd pour out this 0.68 liters, and then you'd add water until it got up to that 3.4 liters that you're looking for. And once you did that, you'll end up with exactly a 2.4 molar hydrochloric acid solution. And that's how you basically work out a simple dilution problem. So let's take a look at another guy here. Let's try another one out. And so this one says, how many milliliters of water must be added to 470 milliliters of a 7.6 molar sodium chloride salt solution to create a 1.0 molar solution? We're going to set this up the same way we did before. Is that our first solution, it says, is a 7.6 molar. So I say 7.6 molar solution. And let's see what we know on this one. Do we know the number of moles of salt, the number of moles of solute here? Doesn't say anything about that. So we'll say this is going to be X moles on top, divided by, do we know how many liters of the 7.6 molar solution. It said how many milliliters of water to be added to 470 milliliters of the 7.6 molar solution. So we do know the number of milliliters. And remember that to go from milliliters to liters, we're just going to move the decimal place over 3 spots. And so we'd get 0.470 liters. Technically just 0.47. We really don't need that 0 there technically because that's not significant. So I'll take that off really quickly. So 0.47 liters, just like that. And so this is my first guy right here. Now let's look at our second equation. Our second one is our other concentration, which is a 1.0 molar solution, equal to the number of moles of the solute, number of moles of salt. In this case, don't know it, so X moles is what we have here, divided by the number of liters of solution. Do we know what that is? Doesn't say how much of that either for the 1.0. And so we'll say we have Y liters here. Of these two, we can solve the original, the 7.6 guy, because it only has one variable over here. And so to do that, we'll multiply 0.47 on both sides. So times 0.47, that's a multiplication guy right there. So times 0.47, 0.47. And so if you go ahead and take that in your calculator, you say 7.6 times 0.47, and I get a 3.572. So I get that X equals 3.572 moles. I can then, once I've got that, take that 3.572 and put it into our other equation. So I get 1.0 is equal to 3.572 moles over Y liters. And so at this point, go ahead and multiply the Y on both sides. So multiply a Y on both sides here. That's going to cause my Y's over on the right to cancel. And so I just have 1 times Y, which is just Y, is equal to 3.572 liters. All right. Now, taking a look at this, the question asks what? It says, how many milliliters of water must be added? It didn't ask for the amount of solution. And what we've got over here is that we need 3.572 liters of the 1 molar solution. That's how much we're going to create. But the question asks for how much water we have to add. Well, in this case, we started with 470 milliliters. So we started with 0.47 milliliter or liters of our water here, and we're going to go until we get our new guy, which is 3.572. So that's a 7, 2. So in order to figure this out, remember, whenever we're doing dilution, we never add solute. All we do is we add solvent. We're adding water. And so to go from 0.47 to 3.572, we'd have to only add water there. And so to find the amount of water, we're just going to take the difference. So we take 3.572 minus the original 0.47. And in doing so, we get 3.102. And so 3.102 liters of water would be added. Significant figure-wise, taking a look at what we've got along that, is that we start off here, 7.6 molar has 2 sig figs. The 470 milliliters also has 2 sig figs. That means our answer for X would have 2. Putting it over here, that means this guy has 2. Our 1 actually just has 2 right here, so our answer for Y would have 2. That would mean it'd be rounded to the 10th place right here. And so that's rounded to the 10th place for liters. So that means whenever we do a subtraction here, it'll also be around the 10th place. So our final answer on this would just be 3.1 liters of H2O would be what we get for our final answer here. And so that would be how you set up a dilution calculation whenever you're dealing with sort of adding water. So one last example to make sure we understand it pretty well here. 70 milliliters of water are added to 250 milliliters of a 6.0 molar solution. What is the concentration of the diluted solution? So setting this up again, we're going to once again write out 2 equations, one for one solution, one for the diluted solution. So the only one we really know here is this nice 6.0 molar. And so we're going to say we start off with 6.0 molar solution. Do we know the number of moles of solute? Doesn't say anything about that. So it'll be once again X moles, as it's almost always going to be on these problems, divided by the number of milliliters of solution. So of the 6.0, how many milliliters of solution do we have? It says added to 250 milliliters of a 6.0 molar solution. So if we have 250 milliliters, that would simply be 0.25 liters, like this. And that sets this guy up. For our other equation, do we know what the concentration is? Let's take a look. So, because of the fact we don't know what the concentration is, we're just going to use that as y. And so we have y molar solution, whatever that is, equals the number of moles, which we don't know for this one either, so x moles, over the number of liters of solution. And it says right here is that do we know that? Well, it says we started off with 250 milliliters of the 6 molar solution, and we added 70 milliliters of water, and so that would mean our total solution would now be 320 milliliters. And so if our total solution is 320 milliliters, then we'd have a 0.32 liters down here. Of these two is that the one we just did, the y molar solution, the unknown molar solution, we have two variables, both y and x. Can't solve that one. For our other guy, the 6 molar solution, is that for that one we only have one variable, just the x. And so let's go ahead and solve that. Multiply both sides by 0.25. And so we do 6 times 0.25, and so in doing that we get 1.5 is equal to x. And so that's 1.5 moles is what we have here. We'll take that, plug that into the other side, and so we get that y is going to be equal to 1.5 moles over 0.32 liters. And so go ahead and once again get out our calculators there, and we say 1.5 divided by 0.32, and so we get 4.6875. And so for the whole thing out, 4.6875 molar solution, which would make sense because it originally was at 6 molar solution. We've added water, so it's diluted it a little bit. So now it's down to 4.6875. Significant figure-wise, taking a look, we have the 6.0 molar, 2 significant figures. The 250 milliliters, 2 significant figures. Other one was the 320 milliliters, or 0.32, over on the other side. For that guy right there, we basically had to add up our 250 milliliters, which is round at the tens space. The 70 is spelled out, and so as a result, it doesn't really affect anything. It's got infinite significant figures. So that means our 0.32 will also have 2 significant figures, which means that since our 1.5 would have 2, this has 2 down here. Our answer is just going to have 2. And so our final value for this would be simply 4.7 molar solution. And so by adding our 70 milliliters of water to our 250 milliliters of a 6 molar solution, we end up with, quite simply, just a 4.7 molar solution.